We continue with section 2.3. We are going to be proving theorems about the inverse of a matrix. So I start here with theorem 2.9 about the inverse of a product of matrices. So if A and B are invertible n by n matrices, then we are going to prove that the product AB's inverse is B inverse times A inverse. So recall an inverse, if you multiply it by the matrix on either side, gives us the identity. So in our proof, we are going to start with matrix AB and multiply it by B inverse A inverse and see how that works out. And then we're going to multiply in the other order and see if we get the identity both directions. Then we can say that this B inverse A inverse is in fact the inverse of the product AB. All right, our first step uses the associativity property of matrices. So we can say this is A and then in parentheses times B inverse times A inverse. And we know B times B inverse is the identity matrix. So this is A times the identity times A inverse. And we know A times the identity is just A. So this is A times A inverse, which is just the identity matrix. All right, let's switch and go in the other direction. So now we are going to multiply B inverse A inverse times the product AB. And again, my first step is to use associativity and rearrange this order of multiplication here. And so now I first multiply A inverse times A, which is going to be the identity. And then B inverse times the identity is B inverse times B, which is also the identity. So we have shown that if you multiply B inverse A inverse times either side of the product AB, you get the identity back. So that is the definition of being an inverse. So we have shown that the inverse A inverse is the inverse of the product AB. All right, let's go to theorem 2.8. I'm doing this out of order because here, when I prove theorem 2.8, I'm going to use in part 2 that result that we just found in 2.9. So in our proof, let's first prove the first property here. So in all these properties, we're supposing A is an invertible matrix, A is a positive integer, C is some non-zero scalar, which is just another way of saying constant. So we are going to show then that A inverse, A to the K, C times A, and A transpose are invertible, and all of these properties hold. All right, so step 1 is saying that the inverse of A is just A itself. All right, so by definition, the inverse of A inverse is a unique matrix and I will call it B that satisfies A inverse times B, where B is the inverse of A inverse, equals the identity, and B times A inverse has to also equal the identity. All right, well, let's try out A inverse times A here. So A inverse times A equals the identity. And A times A inverse also equals the identity. Well, the inverse of the inverse, B, is a unique matrix. So then since A is the inverse that works here, then that tells us A is the inverse of A inverse. And this is really proved by this uniqueness of the inverse itself. So you could say, in other words, A equals A inverse inverse, because we only have one inverse matrix. All right, let's go prove property 2. So property 2 says A to the k's inverse is the same as A inverse to the k. All right, so we are going to do this by induction. So when we do an inductive proof, we always start with the case when k is 1, and then assume it's true for k and build on that. All right, so this is going to be a proof by induction. So we check the k is 1 case. So when k equals 1 here, A to the k to the negative 1 power is A to the 1 inverse, or negative 1 power, however you want to describe it, which is just A inverse, which we can say, well, that's A inverse to the 1, which in this case is A inverse to the k. Just squeeze it in there. All right, so now we are going to think about if it's true in the kth case. So if A to the k inverse equals A inverse to the k, then we are going to investigate the k plus 1 case. So then A to the k plus 1 inverse equals, by our exponent properties, we could take this one and say A to the k times A to the negative 1, except it reverses by our exponent properties. So I put my k in the wrong spot here. All right, so that's A times A to the k to the negative 1. And then by theorem 2.9 that we just proved, we can say, well, this is A to the k to the negative 1 times A to the negative 1. Go back and look at theorem 2.9 here. We just showed the inverse is the second element of the product inverted times the first element of the product inverted. So that's all we're doing here, is taking that A to the k to the negative 1 and then A to the negative 1. And then we know, well, this is just A to the negative 1 k times and it's multiplied by A inverse. So this is just A inverse times A inverse times A inverse now A plus 1 times, which is just A inverse to k plus 1. So using mathematical induction, we are able to conclude that A to the k inverse equals A inverse to the k for all positive integers k. All right, let's go on to part 3 here. So part 3 is that if we multiply by scalar c, c times a's inverse is 1 over c times a inverse. All right, so let's check and see if this right here is in fact the inverse just by multiplying it by CA. So we'll go the forwards directions and the backwards directions, or left and right. So CA times 1 over CA inverse. By associativity, we can, actually we don't need associativity, we can just pull the constant out front because it's a scalar. So by our scalar properties, we can say C times 1 over C times A inverse. And so that is 1 times the identity, which is the C identity. The C times 1 over C gives us the 1, and the A times A inverse gives us the identity. And then we check on the other side. So we check if we multiply 1 over C times A inverse times CA, what are our results? So these results are going to be 1 over C, and we can pull the scalar C out front, times A inverse times A. And so this is, again, 1 times the identity, or just the identity. So we can conclude then that this right here, 1 over C times A inverse, is in fact the inverse of the product CA. And now let's prove this fourth property. So the fourth property says A transpose inverse equals A inverse transpose. All right, so we are going to check to see if we take A transpose, here's our proof. We take A transpose and multiply it by A inverse T. Let's see what happens. So we know that we can pull these together under one exponent, making sure we change the order of A inverse AT. And then we know, well, that's just the identity. And the identity transpose is still just the identity. And then we go in the other direction. So we take A inverse transpose multiplied by A transpose. And then again, we can pull these together under the exponent T, but reversing the order. So this is A inverse transpose. And again, we have the identity transpose, or just the identity. So by the uniqueness of the inverse, we have proven that A transpose's inverse is A inverse transpose. Okay, we'll do a couple more proofs in the next video.